So imagine we're going to talk about the position Hilbert space, which is described by, let's say, discrete position eigenstates. Let's just take a step back a second. And let's say we know all of the probability amplitudes. We know all of these coefficients associated with every position eigenstate. Basically, we have pairs of numbers. We have position eigenstate and the associated probability amplitude. And the natural thing we'd like to do here is probably plot them into a graph. So let's do that. So here's an example I've concocted where we're plotting the coefficients C sub n, the probability amplitudes versus the position eigenstates, the discrete position eigenstates. And this, as I said, is taking a step back, but it's just trying to visualize it, and hopefully that'll be helpful to you. So we're simply plotting, let's say, x sub 1 and the corresponding coefficient, and so on. Now, of course, the separation of the increment between each of these position eigenstates is simply going to be 1, delta n. So what will happen when we shrink delta n down such that it is infinitesimally small? Here's our answer. We're still plotting the inner products, but the thing is, they actually form, as we can see, they form a continuous state, which can be clearly expressed as a function of x. The position eigenstates are no longer discrete, they're continuous, so we can actually come up with some sort of an f of x to describe the coefficients associated with our arbitrary abstract quantum state. And the function of x that we use to describe them is known as the wave function. And in fact, the wave function I've used here is given as the square root of 30 over 5 to the 5th, then x outside of 5 minus x. So that's the wave function to describe the continuous set of probability amplitudes or coefficients associated with their arbitrary abstract quantum state living in position Hilbert space. That's this guy here. And this is crucial. If you understand that, you now know what a wave function is. It is the function used to describe the continuous form of the probability amplitudes of our arbitrary abstract quantum state where the basis states are continuous as opposed to discrete. Now, to close, briefly I'd like to show you an alternative way of getting to the same thing, and this one's using a bit more of Dirac algebra. So you might know that if you take what's known as outer product, or the sum of the outer products of your discrete basis states, and you sum them, you can get 1. Now, if we have continuous basis states, then it's going to be an integral of the outer products. And we're talking really about projection operators, though I don't want to get bogged down in that. Anyway, that's basically saying the coefficients must sum to 1, and that makes sense because they're related to the probability. So let's take an arbitrary abstract quantum state living in position Hilbert space. We can always multiply it by 1, which we can do, but we have now a way of re-expressing the number 1 in terms of an integral of the outer products of our basis states. And these are continuous basis states. But if you look closely, we actually have an inner product between the bra x, the basis states x, and ket f sub x, which is our arbitrary abstract quantum state living in position Hilbert space. But that's nothing else except what were the C sub n's in our discrete form, but are really our probability amplitudes. What's that? But none other than our wave function. So we can write our arbitrary abstract quantum state living in position Hilbert space. Because of the continuous position eigenstates, it can be rewritten like this.